Okay. And at the very least, I wanted you guys to understand the context. And so you've had enough time to read it and kind of understand what's going on. If we talk about part A real quick, they want us to create a confidence interval, and this would be for a difference of means. So without doing everything for this, I'm not even going to calculate it, but I would just remind you that it's going to be the test statistic, or it's going to be the statistic plus or minus your critical value times your standard error. So we're going to be looking at x bar sub 1 minus x bar sub 2 plus or minus your t star times your standard error for this is found in your packet. It's going to be s sub 1 squared divided by n sub 1 plus s sub 2 squared divided by n sub 2. So that would be where you're plugging your numbers into. And as far as your sample size go, you can find that up here in the prompt. So that would be your calculation. You would want to check your assumptions, go through the full process. So this would be like, maybe it's good to see what an FRQ actually looks like from AP's perspective to say, oh, it's really just this right here. And they're asking me to do all that work based on that one small question. The next part is where it gets maybe more tricky because this is kind of mechanical almost. Confidence interval, here's what I do. Let me just show you. But the next one, we really have to think through this. So an assistant principal reasoned that a much narrower confidence interval could be obtained if the students were paired based on their responses. For example, pairing the 6th grade student and the 7th grade student with the highest number of minutes spent on homework, the 6th and 7th grade student with the next highest minutes, and so on. Is the assistant principal correct in thinking that matching students in this way and then computing a matched pair's confidence interval for the mean difference in time spent on homework is a better procedure than the one used in part A? So remember, you initially have a random group of homework times. I'm just going to use 3 6th graders and 3 7th graders. And it doesn't matter the order that we put these guys in. So what we are suggesting is let's superimpose an order onto this. And now we're going to put the highest right here. So I'm going to put 1 being first place and highest, and now 2nd and 3rd. And I'm going to compare that to the 1st, 2nd, and 3rd in 7th grade. And then I'm going to get a difference between these. So I'm going to create a new column. It's going to be the x sub 1 diff, x sub 2 diff, and x sub 3 diff. So just to make sure everyone's on the same page. Is this a valid way of approaching it? Okay, got a yes. Well, yeah, Eli said yes, so you have to say
No.
no, absolutely not.
I'm trying to be reasonable.
All right. So does anyone have any thoughts on this though? Okay. All right. I just want to give you guys time to kind of, at the very least, think through it. Maybe now you can start coming up, even if you're not going to share, you can come up with some thoughts that you might be having in your own head on this. And I'll admit for myself, this would be a problem where it's tough to know. Does that make sense? Now, luckily, this is an old FRQ. There's an answer key. I looked up the answer key. So let's understand a little bit more conceptually about what's going on with this. So if you have if you do it this way, what you're doing is you are creating a kind of an order or a pairing of data points based on the original response variable. And we're essentially saying, let's gather all the data. Once we have it, then let's order it and pair people up based on that. But there wasn't a natural pairing of these people ahead of time. So there's kind of 2 problems with this. And so the answer is that this would not be an appropriate thing to do. That's a short answer. Yeah. There you go. Leo had it right. But the 2 reasons for it, one of them is that if you were going to match people based on some characteristic, then that needs to be determined ahead of time. You can't do it after you've collected your data and decide to kind of almost arbitrarily pair people. So yeah, that's one reason why this would not be a fair thing to do. The other thing is that, like I was kind of hinting at and saying before, if you're going to pair people, pair two data points, then there has to be some kind of a independent reason why you're pairing them together, not just based on their response variable. So in this case, it was how much time they spent doing homework. Well, maybe you pair them based on other qualities first. Like we're going to look for, maybe their grade, I guess you don't have a GPA in junior high, but whatever their current grades are in class. You know, if you wanted to pair it that way first, say everyone who's making all A's are going to be paired with an all A student. So if you decide that, but you can't decide to pair based on the response variable alone. So it's a conceptual thing. It's kind of weird. And I can honestly say it's not something we really talked about in the past. So that's why I wanted to go through this FRQ. All right, are there questions about this one? All right then. Well, just as a side comment, there will probably be some kind of conceptual question that shows up on the test where it's something we might not have ever talked about like this one, or something that you forgot because it was kind of this brushed over conceptual thing. And that will happen. You don't need to be shooting for a 100% on the AP test. I think I've mentioned in here, but 50% is a 3, 60% is a 4, 70% is a 5. So if you feel like you can get 70 on a 70 on this test, you've got a 5. And if you feel like you can get half of it right, then you've got a 3. So I don't want you to stress out on any one particular problem. So if this one you're like, I just got to do my best and come up with some reasoning that makes sense to me, maybe you'll get some partial credit for it. All right, I've talked enough about this. Let's go ahead and move forward.
There's like something you can look up online and we'll do it for you.
Yeah, you'll have to talk with people to learn more about that. So one thing I wanted to mention real quick before we jump into our practice for today is that I haven't been mentioning it to you guys because we're still going through content and learning, but you're certainly welcome to show up to this. If you are doing the AP test and you want to get some extra practice, Wednesday and Friday morning, I am meeting with students starting around 7:10. We really don't get started until like 7:15. But for the first, those 45 minutes before class starts, we're meeting, we're going over packets. All the stuff we're going over now is stuff that you've already seen. Pretty soon we're going to be looking at some new content that you maybe haven't seen yet, but there's not much new stuff left for us to see. But anyways, if you want to show up for that, just get some extra practice, and you can show up via Zoom, you can show up via in person. Let me know, and I will include a link, the Zoom link in the Canvas class so that you guys can look at that, or you can follow that link if you choose to show up. Certainly no expectation for you to do so. And I also wanted to show you real quick that the packets that I've been creating for them, I'm also making those available for you. This is not an assignment that anyone needs to worry about doing, especially if you know you're not doing the AP test, then you can kind of ignore what I'm talking about right now. But at the very top of your modules, I added a new, I hope this is available. Yeah, okay, good. It should be available. It says AP Statistics Review. And you can see review 1, 2, 3, and 4. We just had our 4th meeting, and the packets will just be a little bit of, if we look at one of them real quick, I don't want to spend too long looking at this stuff. So the first couple pages are going to be like review of terms and just main ideas from, in this case, experimental design. So all the different types of sampling methods, the experimental design notation. Here's an experiment. And then all this fun stuff. I'm going to skip through this. And then the next part of it will be a bunch of multiple choice questions. It's going to be about 25 or so on average. So this seems like a huge packet, but part of it, if I scroll down far enough, now there's some FRQs that you can practice with. And then the very last part of this is going to be an answer key to the multiple choice questions. So if you want to show up and get some help and kind of be available, be present for that, that's a good idea. But this is just going to be something that's a resource that's available for you. And it's a really good idea to run through these multiple choice questions. And some people are really good if you get this one wrong, but then you can see what the correct answer should have been. Some people are really good at kind of learning just from those mistakes and saying, oh, now I get it. It should have been census because now that makes sense. And why? Anyway, some people are really good at kind of figuring out where their mistakes were. But if there's some of them you look through and you don't know why it's the wrong answer, you still don't know why E is the right answer and not C or whatever, then that's something you can bring back to me. And we're in class together, so you can say, hey, can we hang out after class is out? Because I have some questions. So anyways, a little bit long-winded there, but if you want to take advantage of those resources, in addition to those progress checks that are available, that is a good kind of practice for you. And now let's practice with chi-square. Was there anything else I was supposed to mention? Yes, there was. One last thing I was supposed to mention is, and you've probably heard this in other classes if you're in an AP class right now, but if you are a senior and you are part of the AP Academy and you want to petition to graduate from the AP Academy based on whatever level you achieved in there, I will post in the chat the link to the Google form, and you can follow that. Maybe just pull it up in your browser and you can fill that out at some point. Okay, so if there are any questions about that, let me know. I believe that's everything housekeeping that I should have run through. So let's start going through this. Let me make sure I didn't skip a screen. No, I didn't. Okay, maybe I'll pause right here and see if there are any questions on anything right now. I'll assume there are not. So let's look at this. Carrie made a 6-sided die in her ceramics class and rolled it 90 times to test to see if each side was equally likely to show up. The table summarizes the outcomes of her 90 rolls. So we want to state the hypotheses that Carrie should test. And as far as a goodness of fit test goes, our hypotheses are always the same, which is the null hypothesis is that the claimed distribution is true. And you can summarize it that way. So we're not writing an equation for this. I talked about this yesterday. But the claimed distribution is true, is our null hypothesis. The alternative, we don't have a direction as far as this goes. We don't say it's not true greater than, it's not true less than, or anything like that. It's just either the claimed distribution is true or the claimed, I don't know why it's so hard for me to write that word, distribution is not true. And let's put this into context a little bit. We're saying the claimed distribution, it doesn't have anything claimed right now, but if we have a die, what would the claimed distribution of a fair die be? Say that again. Oh, 15 on, okay, I didn't hear the number, 15 on each side. Yeah, so essentially they should all roll the same amount in the long run, right? So each number, so here's the claim, is that each one of them should roll 1/6 of the time. So we can just leave it. It's honestly the null hypothesis written like this, the claim distribution is true, is fair to say, but maybe we could add a little more context to this, say each side rolls 1/6 of the time in the long run. And I wouldn't, well, as far as the alternate goes, we could say the sides do not roll evenly in the long run. Something to that effect. I just lost my stylus. There it is. All right. So those are our hypotheses. There is a reference sheet for this unit that kind of reminds you of what your hypotheses are for each type of test that we're going to learn. There's 3 chi-square tests. They all, well, let me not jump ahead to any of the other ones, but the chi-square statistic will be consistent for each one. So now we need to calculate the expected count for each of the possible outcomes. All right, so what the expected count would be if each one of these rolls 1/6 of the time, and there's 90, and Leo already did the calculation, but what we're saying here is that I want to take this 90 and multiply it by all the probabilities. Now this is great because all the probabilities are the same. We only have to do one calculation. Sometimes you're going to get a distribution where it's not a flat one. So if I get rid of all this stuff real quick, then the expected counts, I'm kind of continuing this table down below the line. The expected counts would be 15 for each number. And remember what a chi-square test is doing. We only learned it yesterday. The chi-square test is basically saying, is the outcome that we got out of 90 rolls so far off of what we expect that we have to reject the null? Because right now we can see that 2 seems to be favored. Now, is it so far out of what we might expect from randomness that we have to reject that it's a fair die? Or is that something that could happen? 90 rolls and you get one number 28 times. That could happen, even with a fair die. So we're going to mathematically determine if this is something we would want to reject, that it is a fair die. So there we go. We have our expected count for each of the possible outcomes. And now we want to calculate the value of the chi-square statistic. Yesterday, we went through and we created the table. We did and let me remind you, the chi-square statistic is the sum of your observed minus your expected, and that difference squared all over the expected. We would have to calculate this 6 times and then add up all those chi-square values. So instead, to make our life a little easier, what I'm going to do is I'm going to take these 6 values here and put that into list 1. I'm going to take these and put that into list 2. And then I can do a chi-square goodness of fit test on the calculator. So yeah, in order to calculate this, we do need to know the degrees of freedom. Otherwise, we get an answer that could be a little bit off or quite a bit off. So remember that your degrees of freedom is your number of categories minus 1. So how many categories do we have here?
6.
There are 6 categories. Okay. So there it is. Now I am going to show you what you need to have in order to kind of show your work clearly. Because remember, a part of doing an FRQ related to stuff like this is to show your work, not just show an answer. Now you probably have your answer. I'm going to go ahead and write down right here, chi-squared equals and P equals. So just like in our previous test, we would have had like T as our test statistic. So T equals or Z equals. Now our test statistic is a chi-square. So I can just put chi-square right here equals. And that's what you're going to report. So I'm going to leave that there, and you guys can fill in what you were able to find using the goodness of fit test on your calculator. All right, there's the p-value. .4. There it is. And I do want you to notice when you do the tests on your calculator, look at that contribution. The one number that we thought was way out of line was this, oops, I didn't want to erase things. The one number that was way out of line was this 28. And if I go to the second number, I can see the contribution. So that contribution for the first category was 0.6, not a big contribution. The contribution from the second one is 11.3. So out of the 14.4, 11.3 came from that number 2 being out of line. So that's really good. And for certain conceptual questions, it's going to be important to state why the chi-square statistic is so big. And just as another reminder, the bigger your chi-square is, the more likely you are to reject the null, which is kind of the same thing as our T and our Z. If we had a really big Z-score, Z-test statistic, then we'd say, okay, that's going to be a low p-value. Same thing here. The bigger this chi-square is, but of course it changes. And now I've said enough on this. So the question is, what work do we show exactly? And we will do this more, but the work that we want to show is this right here. I can show the very first calculation that I have to do and the last one, and then I can show what that equals as far as my chi-square. Now, I know that doesn't make sense a whole lot right now, so let me show you what that looks like for this problem. The very first calculation I'd have to do using this equation would be, and actually specifically I'm going to focus on this part, the observed minus expected. It would be 12 minus 15 squared divided by 15. Plus, so that was the first one, because notice there's the 12 was the observed value, 15 was the expected, and I just filled that in. So are you guys with me on that? Okay, so I showed the first one. If I want to write this entire thing out, it'll take me a while, but I'm going to put dot, 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 plus, and then I'm going to jump to the last one. So now it's 15 and 15, so it's going to be 15 minus 15 squared divided by 15. So if I show the first one that I would have added and the last one that I would have added, then it's understood that was the entire calculation. And this is where I got 14.4. So that's a good way of showing your work. Now, I know we didn't check our conditions yet. We're going to do that in a little bit. I'm doing this a little bit out of order today, but I wanted to just jump into this. Okay, so which degree of freedom should you use? We already talked about that. Find the p-value. Now it says find table C. If we do go, now we know the chi-square value. We already calculated it. But if we go to table C with, what was it, 5 degrees of freedom, find where 14.4 would have lived. Let me see if my next, there it is. It shows up on the next screen. So I'm going to clear everything on the screen right now. There it is. It was shown up right in here. And we already found our p-value of 0.013. So that checks out. Okay. So like we said, calculator or no, you should be able to figure this out, but it's not the kind of test you want to do by hand. So most likely what would happen is certain values would have been reported to you, and then you have to do an extra step. So maybe they'll say you had this situation set up and you got this chi-square statistic. Do you reject the null hypothesis or fail to reject it? And you might have to say what the hypotheses are. You might have to determine the degrees of freedom, and then you might need to use the table to determine what the p-value would be and therefore make a decision on the hypotheses. Okay, but maybe you skip the part where you actually do the calculation. All right. So here are the conditions, and we skipped over this before, but now we'll look into it. The conditions for a chi-square goodness of fit, you're familiar with this? Random, same as always, and we're good to go. The 10% rule is the total sample size should be less than 10% of the population size. So don't worry about the individual category counts. So in our last example, there were 90 roles. Now that automatically doesn't even, we don't need to worry about the 10% because they're independent. But still, it meets the 10% rule. And then large counts. This is one that's a little bit different, but it's not difficult. Every expected count must be at least 5. And so the only one you need to worry about is calculating the lowest expected count. So let me come back to that. So our expected counts from the last one was just 15 across the board. So we met the large counts condition just fine. And I want to emphasize it's your expected count, not the observed. Okay. So are the conditions clear enough? Okay, no worries. We're going to run through another example of this. And so we'll be able to see. And now this is maybe a good example because not everything is a flat distribution like the die was. Now we got some other fun numbers to work with. Do these data provide convincing evidence that the distribution of car color in Oro Valley differs from North American distribution? So Oro Valley, notice we have an Oro Valley sample. It's just one sample. And here's the distribution across North America. So this 84 does not directly mean it's 23%. And we're going to determine if it matches the distribution that we found in the rest of the country. All right, and really, maybe it's a good thing just to wrap your head around it. Look at these numbers. You don't need to calculate the percentages. In fact, you don't want to calculate percentages for this because we're dealing with counts, not with proportions. But anyways, looking at this, does it at least seem like this matches up? Or maybe not matches up? Maybe it doesn't. So we're thinking maybe it doesn't match up. Okay, we can see like certainly the most popular is still the most popular in Oro Valley, and the least popular is still the least popular in Oro Valley. And in between, maybe it switches up a little bit. Maybe it's far enough apart that this is meaningful, and maybe it's close enough that it's meaningful difference. All right. The hypotheses and the significance level. So we can stick with our good old 0.05. And the good thing about hypothesis tests, your significance level, we're still essentially calculating the same thing, a p-value, no matter what. Hypotheses, what's the first hypothesis? What? Okay. I was just create a random hypothesis. Okay. I think that gummy bears are better than gummy worms. I know that's controversial. I'm sorry. I didn't mean to kick the hornet's nest with that one. Now, what's the null hypothesis? Right, that they match, and the way that we, just to keep it consistent, what's the way we phrase that? All right, that's close. And there are different ways you can phrase it. It's not like this is the one way AP accepts, but the claimed distribution is true. And maybe we could change the phrasing of this a little bit. Maybe we could say the claimed distribution of car colors is true for Oro Valley. All right, we could make it specific to the problem, but again, the claimed distribution is true is your null hypothesis. The alternative is that the claimed distribution is not true. All right, fun times, right? I'll pause there in case there's a question, but I'll move forward now, assuming everyone's good to go with that. Name of the procedure, it already has this filled in here. It's a chi-square test for goodness of fit, or the chi-square goodness of fit test, or you could probably even write the chi-square goodness of fit test, and you could probably get away with that, though spell it out just to make sure. Check conditions. What's the first condition, Eli?
Random.
Random. Is this a random sample? Here, I'm going to go back to this so you can read the prompt. Is it a random sample?
Yes.
Yes. Random sample. So is it random? Yes. And if you show this random sample in quotes, that's kind of understood. You're saying, I saw this in the prompt. That's a quote from the prompt, so therefore it's a random sample. 10%. Did we meet that?
I assume you're more than 300. Sorry, that 300 is not 10%.
Okay, so we assume that 300 is less than 10% of all cars in Oro Valley. Safe assumption. We'll say we met it. And the last one, the normal condition, or large counts. But, well, actually, maybe better here to not say normal because we're not creating a distribution in the traditional sense. So we'll just say large counts. All right, so large counts. What is it that we need to calculate for this? Smallest. The smallest expected. So what is the least expected that we're gonna, least of the expected? Green. Okay, so 300 times 2%. I'm just gonna create another row right here. What's 300 times 2%? 6. There it is. So we don't need to show all of them. Now we will need to calculate all of them, so you could do that now. But you really only need to show that your smallest expected count is at least 5. So our smallest expected is 6, and 6 is greater than 5, so we're good. Now we will need to calculate the rest of them, so maybe we can fill the rest of this row in real quick. I'll leave it there, you guys can fill in the rest of it. All right, so we've got all of our expected counts. We will need to know that. Well, technically we need to know it if we're going to calculate this by hand. We are going to let the calculator do the work, but still it's good to show the expected counts because we will need to use at least the first and the last one when we show our work. All right, but we could also show that we calculated all of it. We know what the process is. Now looking at this, maybe we can have a better idea. Does it seem like this is going to be close enough where it falls in line? And if it doesn't fall in line, where is the biggest discrepancy? 38 to 54 is a pretty big discrepancy. Where's another big one? 84 to 69 is big in a raw number perspective. And then this is where, that's why we divide by the expected at the end, because that's going to standardize our scores in a sense. So yes, going from 84 to 69 is a difference of 15, but 15 compared to 69, as opposed to, in this case, 16 compared to 54, proportionally, this one's a lot bigger of a change. And where's another big change going to take place? Yeah, right here at other. And the question is, and we'll answer it mathematically, but maybe you can kind of think for yourself, is this change big enough where, you know, it would cause us to reject the null? And we can kind of see this makes sense. If you're living in Oro Valley, you might not want to have a black car. So it makes sense there's going to be fewer of those. I had a friend, my first year teaching, a fellow teacher who moved down from Minnesota. And when he was in Minnesota, he bought a black car with black leather interior. And then he moved down here to the valley to teach. And he probably didn't like that decision every single day of his life. But there we go. That we've checked our conditions. Now we can do the work. The specific formula that we're doing, I'm going to erase this stuff down here. All right. So the specific formula is just a chi-square statistic, and that's just right there on the front. So this doesn't change even when we do our other chi-square tests later. The specific formula is still the same. Chi-square equals the sum of your observed minus the expected squared divided by the expected. We'll come back to the picture. The work, we saw how to do this. And I'm going to see if you guys can fill in, can create the work for this problem. All right, this is pretty good for showing the work. Just make sure that you have a couple of things I would change here. Make sure that you have plus on either end with a dot, dot, dot to show that there are lots of other calculations going on that we're just not showing. And second, you might want to put this in order from the first one first and the last one last. But I think that wouldn't be a big deal as far as, okay. It is showing that you're just going in reverse order, so not a big deal. The other thing is now we would actually add it up to see what that number is. And this we would not be doing by hand. So if you not plugged it into your lists, go ahead, do that. We can calculate the test statistic and the p-value at the same time. So go ahead and write those in when you get those. So you guys hopefully ran through, got the stuff put in, and were able to come up with the correct numbers here. I like those numbers. That's what I got. We didn't talk about this. What was our degrees of freedom here? 7. There are 8 categories. And so therefore, 7 degrees of freedom. All right. So the last thing that we need to do right here is it's good to show your picture. Now, what you can see on the top of table C right here is that, and we saw this yesterday, your chi-square distribution is a skewed right distribution that starts at 0. So we don't have a whole lot of space up here, but that's okay. So I'm just going to show this. And what I want to do is I want to show that, and it's just going to be to get the point across. It's not trying to be exact about anything. If my critical value for significance is somewhere right here, well, let me not worry about that. Let's just say that our 29.92 would be my chi-square value right here. And then the probability right here, anything to the right of it, that would be the p-value. So just drawing a quick diagram showing that this is a very extreme value, and it's just to get the point across. Okay, so we've done all the calculations. We are ready to come up with a conclusion. All right, now we could also use the table with 7 degrees of freedom. 29.92 is off the chart to the right. Notice that 26.02 is the biggest it gets. So we're going to be below. So we could have also used, just to show you, our p-value will be less than 0.0005 if we were using the table. Okay. So with that, we are now ready to conclude this. And I'm going to clear the screen. All right. And luckily, we can use the same formatting that we've used for all of our conclusions before. Because the p-value was less than our significance level, and here's where you can put in the numbers. So blah, blah, blah is less than 0.05. We reject the null hypothesis. There is convincing evidence that, well, that what? The distribution of car color in Oro Valley differs from the North American distribution. So this, I would just copy, and paste right there. I'm not going to write it out, just to save on time. All right, so the next question right here says, if there is convincing evidence of a difference in distribution of car color, perform a follow-up analysis. What do you think they're asking for here? Okay. And so the thought was, what are some evidences for it? Not necessarily like us trying to come up with why it's different. I mean, we might assume that there's going to be fewer black cars because people don't want black cars in the desert, but that's not what they're asking for. What could we talk about to answer this question?
Maybe that we could get a bigger sample size that might reflect the distribution a little bit better.
That's a thought. That's not what we're going to need to do. So let me just go ahead and answer it since we're running short on time. This is where we can look at the contributions. All right. So we can see, why is this chi-square statistic so big? And we threw out a couple of them. We said that that first one was off. What is that? 3.26. So out of the 29.92 that we got, 3.3 of it came from the first category. If I scroll over more, what is it? 4.7 came from the second category. And we want to find, like, what was the biggest contributor? The third category was a 6.0. But if I go all the way over to the end, it's a little bit annoying having to scroll over this far. I'll just keep going. If we go all the way to the end, look at that. The last category, the one that we were saying with other, that contributed 15.4 to our chi-square statistic. So what we can say is, this doesn't match primarily from these categories. All right, so yeah, the black, gray, and other especially did not match up with the national distribution. Okay, Does that make sense? I'm not actually writing it out, but okay. Checks out. Good. If there are questions, you can always approach me and ask those. If you ask nicely. No, just kidding. There's not going to be any new homework today. So this is just a continuation of what we were doing yesterday. So if you didn't do those homework problems, I would highly recommend doing it. And then we're going to learn 2 more chi-square tests on Thursday and Friday. So that's some good news, right? All right. So if you read through the chapter, you'll be able to get a head start and understand a little bit about this test for homogeneity. We'll do that tomorrow. In the meantime, have a wonderful day. And yeah, I got nothing more to say. Have a good one.